In 1957, a 27-year-old graduate student at Princeton wrote a doctoral thesis that said something no physicist in the world was willing to say out loud. He said, "The equations mean what they say." That's it. That's the whole idea. He added nothing, he removed nothing. He didn't propose a new force, or a new particle, or a hidden layer underneath the visible one. He simply refused to look away from what the mathematics of quantum theory had been stating plainly, in public, for 30 years, that when a quantum system has more than one possible outcome, all of them happen. Every one of them. Permanently. Forever. And if he was right, then nothing in this universe is ever singular. Not particles, not events, not decisions, not you. There is no such thing as a possibility that gets spent. No such thing as a road not taken. Every road is taken. Every version of every moment is somewhere out there, fully real, still running. Now, hold that thought, because here's what happened to the man who said it. Within a year, the most powerful physicist alive had humiliated him. Within 2, he had quit physics permanently, at an age when most theorists haven't started their real work yet. He took a job at a defense contractor outside Washington, and he spent the next 23 years calculating how many millions of Americans would die in a nuclear exchange, and in what order, and from what. He drank, heavily, daily, from lunch onward. He smoked around 100 cigarettes a day. He gained an enormous amount of weight. He was, by every account that survives, physically present in his home and almost entirely absent from it. A man who could sit at the dinner table with his own children and not be reachable. He died of a heart attack on the floor of his bedroom at the age of 51, and his 19-year-old son found the body, and later said that it was the first time he had ever touched his father. And he had left instructions. He had told his wife that when he died, she should throw his ashes out with the garbage. She did. Not immediately. She kept them in a filing cabinet for a few years first, because how do you actually do a thing like that? But eventually, she did exactly what he asked. Today, his idea is taken seriously by a large fraction of the people who work on the foundations of quantum mechanics. It is taught. It is defended in print by some of the most respected physicists alive. It has a 50-year literature. It has probably shaped how you personally imagine reality, even if you've never heard his name, because the phrase parallel universes leaked out of his thesis and into every science fiction franchise of the last 4 decades. He never knew any of it. He was dead before the Vindication started arriving in force, and he had stopped caring long before that. His name was Hugh Everett III, and this is the story of a man who proved that nothing is ever lost, and then lost everything. I want to say one thing before we start, and it isn't cheap intrigue, it's a genuine disclaimer. This video has a dark ending. Not a spooky ending, a sad one. There's a death in this story that I'm going to handle carefully and without detail. And if you're in a fragile place right now, this might not be the one for you. I'd rather lose the view than be careless. Still here? Good. Let's go. The book this is built on is called The Many Worlds of Hugh Everett III by a journalist named Peter Byrne, published by Oxford University Press in 2010. And I want you to hear the subtitle, because the subtitle is the entire film. Multiple Universes, Mutual Assured Destruction, and the Meltdown of a Nuclear Family. Read that again. Multiple Universes, Mutual Assured Destruction, and the Meltdown of a nuclear family. 3 completely different registers: cosmology, Cold War strategy, and domestic catastrophe. And Byrne is telling you up front that in this one life, they are the same story. Here's how the book exists at all. Everett's papers, the drafts, the letters, the notebooks, the unpublished work, sat for 25 years in cardboard boxes in the basement of his son's house in Los Angeles. Some of them were moldering. Some had been in a flood. A physicist and a journalist eventually went through them, and what came out was the first real portrait of a man that his own family described as essentially unknown to them. I should be honest about my relationship with this book. It is not a fun read. Byrne is meticulous to a fault. There are stretches about defense procurement contracts and operations research committees that made me want to lie down. And Byrne clearly likes his subject more than his subject deserves, in places, and then punishes him in others. But it is the only serious biography that exists. It is built from primary documents rather than legend, and it does something I've almost never seen a science book do. It refuses to let you have the myth. Every time you start to feel the romance of the misunderstood genius, Byrne quietly puts another document in front of you. A letter, an interview, a memo that complicates it. And there's one more source I'll lean on later, a documentary The Sun made in 2007. We'll get there. Remember that there's a sun. That's the first thread I'm asking you to hold. Now, I can't tell you what Everett did until you feel the problem he was solving. And the problem is genuinely one of the strangest situations in the history of science. Because it isn't a mystery about nature. It's a mystery about a rule that physicists wrote down themselves and then never explained. Let me build it from nothing. No equations, I promise. Here's the first thought experiment. Imagine a single electron, not a tiny ball. Forget balls. The ball is the thing that ruins everyone's intuition here. Imagine instead that the electron is described by something like a spreading ripple. A wave. Not a wave in water, a wave in a mathematical space. But the key property is the one you already know from water. A wave doesn't have a location. It has an extent. It's spread out. It's here and there and over there, in different amounts. Now send that ripple at a barrier with 2 narrow slits in it, and let it hit a screen behind. Because it's a wave, it goes through both slits. Because it goes through both slits, the 2 parts of it overlap on the far side. And where crest meets crest, you get reinforcement. And where crest meets trough, you get cancellation. You get stripes. Bright, dark, bright, dark. Textbook interference. Nothing weird yet. Do this with water in a tank at a science museum, and you'll see the same pattern. Here's the weird part. You can send the electrons through one at a time. One electron. Wait. Another electron. Wait. Another. Each one arrives at the screen as a single dot. A point. Not a stripe. A dot. In one specific place. Like a bullet hole. And yet, as the dots accumulate over hours, they build up the stripes. The interference pattern assembles itself out of thousands of individual point-like arrivals, each of which had no idea what the others were doing. So the electron travels as something spread out through both slits, and it arrives as something located in one place. The mathematics that describes the traveling, the wave function, Schrödinger's equation, is beautiful, smooth, deterministic, and it never, ever produces a dot. It produces spread out possibility. It says, Here's the ripple, and here's how the ripple evolves. And it's precise to a level of accuracy that is frankly obscene. Quantum electrodynamics has been confirmed to something like 12 decimal places. It is the most successfully tested theory human beings have ever produced, but it never gives you a dot. So in the 1920s, the founders of the theory patched it. They added a second rule by hand. Rule 1. When nobody is looking, the wave function evolves smoothly and deterministically, and spreads out into all the possibilities. Rule 2. When a measurement occurs, the wave function collapses, instantly, randomly, irreversibly, into exactly one of those possibilities, with probabilities given by the size of each part of the wave. And it works. Operationally, it works flawlessly. Every experiment ever done in the last century says the recipe is correct. But sit with Rule 2 for a second, because Rule 2 is not like anything else in physics. Every other law we have is a description of what nature does. Rule 2 is a description of what happens when we get involved. It contains the word measurement, and measurement is not a term that appears anywhere else in fundamental physics. There's no measurement operator in gravity. Electromagnetism doesn't care whether anyone's watching. And now the nested question arrives, and once you see it, you can't unsee it. What counts as a measurement? Is it when a photon hits a detector? Fine, but the detector is made of atoms, and atoms obey Rule 1. Is it when the detector's needle moves? The needle is also made of atoms. Is it when the reading is printed on paper? Or when the paper enters your eye? Or when the signal reaches your optic nerve? Or when you become consciously aware of it? Because every single one of those steps is a physical process made of particles that, according to the theory itself, obey Rule 1 and only Rule 1. So where is the boundary? At what size, at what temperature, at what level of complexity does a system stop obeying the smooth deterministic law and start obeying the collapse law? Nobody could say. Nobody can say now. This is the measurement problem, and I want you to appreciate how genuinely embarrassing it is. Our most precise theory of reality contains a step that is triggered by an undefined event at an unspecified scale by a mechanism nobody has ever observed, described, or written an equation for. Erwin Schrödinger made this point with a cat, and the cat has been so thoroughly memed into oblivion that people have forgotten it was an insult. Schrödinger wasn't proposing a cool paradox. He was mocking his colleagues. He was saying, "Look, your rule lets me chain a microscopic superposition to a macroscopic object. And if you take your own theory seriously, you now have to say the cat is in a smeared combination of alive and dead until someone opens the box. Which is obviously absurd, so please, fix your theory." They did not fix the theory. They gave it a nickname, put it on a t-shirt, and kept using the recipe. And here's the part I find genuinely difficult to forgive. And this is where I stop being neutral for a moment. The dominant attitude that formed around the theory in the 1930s and 40s, the one that gets called the Copenhagen interpretation, after Niels Bohr's Institute, was not really a solution. It was a very sophisticated instruction to stop asking. The mathematics is a tool for predicting the outcomes of experiments. Asking what's actually happening between the experiments is not a physics question. It's philosophy. Move on. Shut up and calculate. And you have to understand, these were not stupid people, and it wasn't laziness. There were serious philosophical arguments underneath it, about the impossibility of describing the microscopic except through the language of the classical apparatus. Bohr was subtle. He was also, by the 1950s, an institution. And a certain kind of institution has an immune system. Then a graduate student showed up, who had grown up on a completely different intellectual diet. Game theory, computers, logic, information. And who looked at Rule 1 and Rule 2 and asked the most obvious question anyone had asked in 30 years. What if you just delete Rule 2? And this is where it gets really interesting. Everett's move is the most elegant thing in this entire story, and it's elegant because it is a subtraction. Look at the competitors. Some interpretations add hidden variables, a real particle riding on the wave, with a definite position all along. Some add a physical collapse mechanism, a new random process that kicks in at a certain scale. Some add consciousness as a special ingredient in the laws of nature. All of these are additions, new machinery bolted onto a theory that is already the most accurate we have. Everett adds nothing. He proposes no new entity, no new force, no new equation. He says, we already have a law. The law is Rule 1. Let's apply it to everything, without exception, including the measuring device, including the laboratory, including the physicist, including the universe. Let's see what the theory says when we simply refuse to interrupt it. And what it says is this. When a measuring device interacts with a system that's in a superposition, say an electron that's in a combination of spin up and spin down, the device does not force the electron to choose. The device gets pulled into the superposition with it. The two become entangled. You now have a combined state. One part where the electron is up and the device reads up, and another part where the electron is down and the device reads down. Add a human observer, and the human joins too. One part of the state contains an electron that's up, a device reading up, and a person who has seen up and is telling you, sincerely, that they saw a single definite result. And another part contains all the same things with down. Both parts are in the equation. Neither one is more real than the other. The equation just keeps running, exactly as it always did. The observer, in Everett's language, is a system that becomes correlated with what it observes. And what you experience as a definite outcome is not the universe collapsing to a single value. It is you becoming one of several equally real records of what happened. He called it the relative state formulation. The state of the electron relative to that version of the observer. Nothing absolute. Everything relative to a branch. That word, worlds, wasn't his. We'll come back to who did that to him. So there's no collapse. There never was. The apparent randomness is not in nature. It's in your address. You don't experience one outcome because one outcome occurred. You experience one outcome because there are now several of you, and each one is asking the question from inside a different branch of the same unbroken wave function. Now, this is the point where about half of you have a very specific objection, and I want to voice it myself rather than let it sit there and eat at you. Because it's the correct objection. You want to say, this is insane. Not wrong, insane. It says that reality is constantly, silently splitting into an unimaginable number of copies. That there are versions of me right now that are identical up to a second ago. That the universe is spending matter and history like an infinitely rich lunatic. And all of this to avoid one extra rule in a textbook? Occam's razor, my friend. The simplest explanation is usually right. and you have just proposed the least simple thing anyone has ever proposed. Right. So here's the response, and I think it's genuinely strong, even if you end up rejecting it. Occam's razor is about the simplicity of your theory, not about the size of the universe your theory implies. It says do not multiply entities unnecessarily. Entities meaning postulates, assumptions, moving parts. Everett's theory has strictly fewer moving parts than Copenhagen. It has one law, where Copenhagen has two. It has no undefined trigger event. The worlds are not an additional assumption. The worlds are a consequence you can't get rid of once you stop hand deleting them. We've been through this exact argument before, by the way, and every time it went the same way. Copernicus was told that a moving Earth was absurd because you'd feel it. Then we were told that the stars couldn't be other suns at unimaginable distances, because that would make the universe grotesquely, wastefully large. Then in 1920, there was a formal public debate about whether the spiral nebulae were clouds inside our galaxy or entire other galaxies. And the modest answer lost. Every single time, the theory that made the universe bigger and humans less central turned out to be the correct one. And every single time, the objection was that it felt like too much. Everett himself made exactly this move, and it's my favorite moment in the whole affair. Years later, a physicist named Bryce DeWitt wrote to him and said, essentially, "I cannot feel myself splitting. Your theory contradicts my direct experience." And Everett wrote back and asked whether DeWitt could feel the Earth moving at 30 kilometers per second around the Sun. DeWitt, to his enormous credit, understood immediately that he had lost. He later admitted that the Copernican reply had got him. Because of course the answer is that classical physics explains precisely why you can't feel it. And in the same way, quantum theory explains precisely why you can't feel a branch. From inside a branch, everything is normal. It has to be. There's no jolt, no seam, no flicker. The other copies of you don't feel like copies. They feel like you, having a perfectly ordinary Tuesday. And that means there is no experiment you can do from in here to tell the difference. Which is either the theory's greatest weakness or its most Copernican feature, depending on your temperament. Now let me be an honest narrator and give you the objection that actually keeps physicists up at night. Because it isn't the weirdness. Weirdness is cheap. The real problem is probability. Quantum mechanics doesn't just say things happen, it says how often. It says this outcome has a 70% chance, that one has 30. And those numbers are confirmed to absurd precision every day in every lab on Earth. But if every outcome happens, what does 70% mean? There's a branch where it happened and a branch where it didn't. One each. Where does the 70 go? You can't just count branches. Counting gives you 50-50 for a two-outcome experiment. Always, regardless of the actual amplitudes. And that is flatly, experimentally, wrong. Everett knew this was the crux. The mathematical heart of his thesis is an attempt to derive the probability rule, rather than assume it. He shows that if you're going to assign a measure to branches at all, and you want it to behave sensibly, you're forced into the standard rule. And then, in the branches with tiny measure, the observers see statistics that don't match the theory. And those observers are, in a specific mathematical sense, of vanishing weight. Is that satisfying? Honestly? Not entirely. Not to me. There have been 60 years of follow-up work on this. Decision-theoretic derivations, self-locating uncertainty arguments, a whole industry. And it is still the joint where the theory creaks. Anyone who tells you the probability problem in many worlds is fully solved is selling something. And anyone who tells you the probability problem in the other interpretations is fully solved is selling the same thing from a different stall. But hold on to that idea of weight, of some branches counting more than others, while all of them exist. It's going to come back at the worst possible moment, in a way that has nothing to do with physics. That's the second thread. I'm keeping count. So, 1956. A young man finishes a 137-page manuscript called The Theory of the Universal Wave Function and hands it to his supervisor. And his supervisor is John Archibald Wheeler. Wheeler is one of the great physicists of the 20th century, the man who popularized the term black hole, who worked on the bomb, who trained Feynman. He is generous, imaginative, endlessly encouraging of young people. He immediately recognizes that his student has done something remarkable. He also worshipped Niels Bohr. He had studied in Copenhagen as a young man. Bohr was, to Wheeler, not merely a colleague, but something closer to a moral authority on the meaning of quantum mechanics. And you can see the collision coming from space. Wheeler wants the thesis accepted. Wheeler also cannot allow the thesis to read as an attack on Bohr. So he does what supervisors have always done, and what Byrne documents in painful detail through the drafts. He edits. He softens. He asks for the removal of the passages that put the knife in. The vivid analogies go. The splitting language gets muted. The direct criticisms of the Copenhagen position get filed down into diplomatic murmurs. The 137 pages become 9. 9 printed pages in the Reviews of Modern Physics, July 1957, under a new and deliberately anodyne title about a relative state formulation, accompanied by a note from Wheeler himself explaining, in the gentlest possible terms, that this brilliant young man's work does not really conflict with the established view, which was not true. It conflicted with the established view the way a demolition charge conflicts with a building. I want to be fair to Wheeler here, because it would be easy to make him the villain, and he isn't one. He genuinely believed in the idea. He pushed it for years afterward. He tried repeatedly to rehabilitate Everett's career. He may also have believed, correctly, that an unedited version would simply have been rejected and would have died completely instead of dying slowly. But the effect was that the idea entered the world already sedated. Everett's own reaction in his correspondence is the reaction of a man being managed. He complies. He is also visibly irritated. And then Wheeler arranges the pilgrimage. Because in that world, if you wanted an idea about quantum mechanics to live, there was exactly one place to take it. March 1959. Everett, his wife Nancy, and their infant daughter Liz fly to Copenhagen. 6 weeks. The plan is an audience with Bohr, and Wheeler has written ahead, warmly, repeatedly, preparing the ground. It was a disaster. The meetings, such as they were, produced nothing. Bohr was in his 70s. His position had been fixed for 3 decades. And the young American was not proposing an amendment. He was proposing that the central conceptual apparatus of Bohr's life's work was an unnecessary appendix. Bohr's assistant, Åge Peterson, argued with Everett and came away unmoved. In the surviving correspondence, Everett's ideas are treated less as wrong than as a category error, a naive American confusing formalism for reality, someone who hadn't understood what the theory is for. Everett later described the trip as doomed from the start. He never seriously tried to persuade the physics community again. And here is the detail from Byrne's book that stopped me cold, and it is the hinge of this entire story. While he was in Copenhagen, in the hotel, in the middle of the failed pilgrimage, having just watched the most important idea of his life bounce off the establishment like a pebble off a tank, Hugh Everett sat down and started writing something else. On hotel notepaper, he sketched the beginnings of a mathematical method for optimal allocation of limited resources. A general technique for answering the question, given a fixed budget and a set of targets, how do you distribute what you have to get the maximum effect? That sketch became a paper in Operations Research in 1963 on the generalized Lagrange multiplier method. It was, during his lifetime, by an enormous margin, his most cited work. It is still used. Think about what just happened in that hotel room. In one motion, a man closes the door on the deepest question in physics and opens the door to applied optimization. Same brain, same afternoon, possibly the same notepad. He was 28 years old and he had just found his second career. And the targets, it turns out, were going to be cities. Everett left physics in 1956, really, and formally in 1957, and he never came back. He was 27. I want you to sit with that number for a second, because in theoretical physics, 27 is not late. Einstein's miracle year was 26. Heisenberg invented matrix mechanics at 23. Dirac predicted antimatter at 26. The field is notorious, unfairly but persistently, for eating its young geniuses and then insisting they peaked early. Everett didn't peak early. He stopped early. There is a difference, and the difference is the whole tragedy. He wasn't out of ideas. Byrne's basement boxes are full of ideas on artificial intelligence, on decision theory, on machine reasoning, decades ahead of their time in places. He wasn't burned out. He was, by every account, still working 18-hour days for the rest of his life. He just wasn't working on this. The standard story is that he was crushed by rejection, and I think that's about a third right. The other 2/3 are less flattering and more human. Everett had a wife and a baby, and no interest in an assistant professorship at a small college on $8,000 a year. He liked money. He liked good food, expensive martinis, sports cars. He had a security clearance and a genuine, unembarrassed enthusiasm for the hardest applied problems in the country. And in 1956, there was exactly one institution offering unlimited computer time, unlimited budget, and the most mathematically interesting problems on Earth: the Pentagon. And this is the turn. This is the point where I have to tell you that this video is not actually about quantum mechanics. The Weapons Systems Evaluation Group was a small, elite civilian and military outfit inside the Pentagon whose job was to answer questions that no one else could answer, using mathematics, not politics, not strategy in the vague sense. Numbers. How many bombers get through? How many warheads are required for a given probability of destroying a hardened target? How the fallout plume moves as a function of wind and yield and burst height. How many people die? Everett walked in as a junior mathematician, and within a couple of years was one of the most important analysts there. His optimization method, the one from the Copenhagen Hotel notepad, was directly applicable, because targeting is an allocation problem. You have a finite arsenal. You have a list of targets with different values and different hardnesses. You want to maximize expected damage. That's a Lagrange multiplier problem. That's what the method was for. In 1959, he was a principal author of a study known as Weapons Systems Evaluation Group Report Number 50. It was one of the most influential classified documents of the early Cold War, and its subject was radioactive fallout. Specifically, an attempt to model, quantitatively, what a full nuclear exchange would actually do to the population of the United States. Not the blast, the fallout, the slow part. The part where the survivors of the first hour then have to survive the next 30 days under a moving sky. The report reached the highest levels. Eisenhower's science advisors read it. It fed into the emerging architecture of American nuclear planning at exactly the moment that architecture was being built. And I want to slow down here, because I don't think the irony has landed yet. In 1957, this man published the claim that every physically possible outcome of every quantum event actually, physically, occurs. Not as a metaphor, not as a bookkeeping device, as a description of what exists. And then he spent the next 23 years computing, in enormous detail, the consequences of the worst thing that could possibly happen to the human species. If he was wrong about the physics, then that work is what it appears to be: contingency planning for a catastrophe that might never come, a model of a hypothetical. But if he was right, if the mathematics means what it says, then those calculations were not hypothetical. Because a nuclear exchange is not one event. It is a colossal chain of events, riddled top to bottom with genuine indeterminacy. A radar return misread, a warhead that fizzes instead of detonating, a wind that shifts, a man in a bunker who decides at 3 a.m. that the alarm is probably a malfunction. Wherever there is real quantum indeterminacy anywhere in that chain, the branches separate. And in a theory with no collapse, the branch where it happened is not a possibility, it is a place. He wasn't modeling a scenario. He was surveying a location. He was drawing maps of a country that, by his own theory, has residents. And I have gone looking, in Byrne's book and everywhere else, for a single line in which Hugh Everett acknowledges this. Any sign that it cost him something, any evidence of a night where the two halves of his brain met each other in the dark. There is essentially nothing. What survives is the opposite. Colleagues describing a man who found the work fascinating, who enjoyed it, who was capable of a joke about megadeaths over a martini at lunch. He was, by several accounts, a hardline rationalist about the whole thing. The position that if you refuse to calculate the numbers, you don't make the horror go away, you just make sure the decisions get made by people who are guessing. Which is a defensible position. It might even be the right one. Herman Kahn was making the same argument publicly at Rand in exactly those years, and getting called a monster for it. And Kubrick eventually built a character out of the type. But there is another possibility, and Byrne raises it carefully, and once it's in your head, it doesn't leave. That for Everett, the horror had been mathematically diffused. That if you sincerely believe every outcome occurs, then the moral weight of any particular outcome quietly redistributes itself into a kind of universal fog. Nothing is prevented. Nothing is caused exactly. All you're doing is adjusting the measure, the weight, on branches that all exist anyway. Remember I asked you to hold on to the idea of weight? Some branches counting more than others, while every one of them is real? That's not just the technical problem in the derivation of the Bohr rule. Look what it does when you let it out of the lab. It is a machine for converting a moral question into an accounting question. It doesn't tell you not to do the terrible thing. It tells you the terrible thing is already being done. Somewhere. by someone with your face. And your only actual power is to nudge the fraction. I genuinely don't know whether Everett thought this way. Nobody does. He didn't leave a diary, and he didn't confide in anyone, which is itself a piece of evidence about the man. But he is the only human being in history who both formulated that idea and then took a job at the exact place where it would matter most. And honestly, if this is the kind of thing that lodges in your head and stays there, the point where physics stops being trivia and starts being a problem about how to live, then subscribing is probably a reasonable move, because this channel is basically a long argument that these questions are not separable. And where we're going next is stranger than anything so far, because there is one more thing about Everett's belief, and it's the part where the biography and the theory fuse into something I find genuinely difficult to look at directly. He appears to have believed that he could not die. Let me be precise about the claim, because this is where a lot of popular accounts go completely off the rails. Start with the physics. If the universal wave function never collapses, then every quantum event with multiple possible outcomes produces branches containing all of them. Fine. Now consider any event that could kill you, and suppose, this is the crucial and highly dubious step, that its outcome depends on genuine quantum indeterminacy. Then there is a branch in which it kills you, and a branch in which it doesn't. Now ask what you experience. In the branch where you die, there is no you to have an experience. There's no observer left in that branch to notice anything. In the branch where you survive, there is. So from the inside, from the perspective of a continuous stream of experience, you only ever find yourself in branches where you survived. Iterate that over every dangerous moment in a life, and the conclusion is that subjectively, you never experience your own death. You experience an increasingly improbable, increasingly lucky, increasingly unlikely survival. Forever. This idea got formalized in the 1990s, most famously by Max Tegmark, under the name quantum suicide, as a thought experiment involving a machine whose trigger is wired to a quantum measurement. And I am deliberately not going to describe the apparatus in any more detail than that, because it is a philosopher's device and not anything else, and because we are about to arrive at a place in this story where I need you to be very clear on that. Everett had reached the essential idea decades earlier, on his own, without publishing it. The physicist, David Deutsch, who met him near the end of his life, has said that Everett believed in the theory completely, personally, in the way most people believe in their own hometown. Multiple people around him report the same thing, that he thought his death, from his own point of view, was not something that was going to happen to him. Byrne quotes family and friends describing this as a settled conviction, casually held, mentioned the way you'd mention your blood type. So let me now do my job and tell you why almost no working physicist accepts the personal version. There are 3 good reasons, and I think all 3 are decisive. First, decoherence and the anthropic sleight of hand. The argument treats survival as a clean binary: dead branch, alive branch. Death is not binary. It is a continuous process, and there is a vast set of branches in which you don't die, but you are catastrophically damaged. The survival branches are not a nice clean set of healthy yous. Most of them are horrifying. The argument quietly deletes the entire middle of the distribution. Second, the measure problem, our old friend. Even if survival branches exist, their weight can be minuscule. If you take probability in this theory seriously at all, then aiming yourself at branches of vanishing measure is not a clever trick. It is the definition of a bad bet. You are not immortal. You are betting your entire existence on the least weighted sliver of reality, and the overwhelming majority of the measure of what, in any meaningful sense, happens, is the branch where you are simply gone, and everyone who loved you has to live in it. Third, and this one is the quiet killer. Almost nothing about ordinary human death is quantum indeterminate in the required way. Cardiac arrest is not a branching event. Atherosclerosis is not a superposition. A body that has been drinking and smoking and sitting for 51 years is running down along a thermodynamic gradient, and there is no plausible branch at any measurable weight where the arteries are clear. Tegmark himself has been consistently clear that this is a thought experiment about interpretation, not a life hack, and that he has no intention of testing it. None of which, of course, is any use at all if the person who believes it is not a physicist evaluating a claim, but a child listening to their father. And now I have to tell you about the family. Hugh Everett married Nancy Gore in 1956. She had typed his thesis. She understood the work better than almost anyone gave her credit for. They had 2 children, Elizabeth, born in 1957, the same year as the paper, and Mark, born in 1963. The household Byrne reconstructs is not violent. It is not dramatic. It is something I think is harder to write about, and much more common, which is a house with a man in it who is not there. Everett worked constantly. He came home and worked more. He drank from midday. He smoked so continuously that the son later described the house as permanently fogged. He had affairs. He rarely spoke to his children in the ordinary sense. Not cruelly, just absently, as though they were a low-priority process he'd get to. Mark has said, publicly and repeatedly, that he had no idea what his father did for a living, and no idea that his father had done anything of importance in physics, until years after the man was dead. Let that land. A boy grows up in a house with the author of one of the strangest and most consequential ideas of the 20th century, and the idea is never mentioned. Not once, in a way he remembers. There was a man at the dining table, doing sums, saying nothing. Nancy held it together. Nancy was the one who kept the papers. Elizabeth, Liz, struggled from adolescence onward with serious mental illness. Byrne documents years of it, and I'm not going to itemize a private person's suffering for content. What matters for this story is one thing, and I want to say it as plainly and undramatically as I can. Liz understood her father's theory. Not the mathematics, the promise. She had grown up inside a worldview in which no one is ever really gone, in which every version of everything continues, in which somewhere there is a father who came home early and asked what you were reading. Hugh Everett died on the 19th of July, 1982. Heart attack, at home, at 51. Mark, 19 years old, found him. In 1996, Liz took her own life. She left a note, and the note said that she was going to another universe to be with her father. I've thought about how to handle this for a long time, and I've decided the only honest thing is to say it once, without embellishment, and then to say what I actually think. I don't think a physical theory killed that woman. Mental illness is not caused by cosmology, and I'm not going to insult her by pretending her life was a syllogism. But I do think this: ideas are not inert. When a father is silent about everything except occasionally a claim that nothing is ever lost, when the one piece of himself he transmits is a doctrine of infinite second chances, And none of the ordinary things, none of the attention, none of the presence, then that idea is not a physical theory anymore. It's the whole inheritance. It's all there is of him to hold. He built a cosmology in which no possibility is ever wasted, and he lived a life in which he wasted almost all of them. And his daughter took the cosmology at its word. Nancy died of cancer 2 years later, in 1998. Mark, in his 30s, was the last one standing, alone in a family of 4. Now let me tell you what happened to the idea, because the timing of it is almost obscene. While Everett was in the Pentagon, the physics quietly turned around. In 1970, a German physicist named Dieter Zeh published a paper on what came to be called decoherence, the mechanism by which a quantum system, entangling with its environment, rapidly loses the ability to show interference. Zeh had arrived at it independently, and when he found Everett's paper, recognized what it was. Decoherence does not prove many worlds, and I want to be careful here because this gets oversold constantly. What decoherence does is answer the question Everett was weakest on. Why don't we see the branches interfering with each other? Why is the everyday world stable and classical looking? Answer: because for any object bigger than a molecule, the environment is measuring it constantly, billions of times a second, and the branches lose contact with each other essentially instantly. The seams disappear on their own. No new law required. That was the missing engine. Also in 1970, Bryce DeWitt, the man who had lost the Copernican argument by letter, published an article in Physics Today that put Everett's idea in front of the entire profession and gave it the name that stuck: many worlds. Everett hated it, or at least never used it. Too lurid, too science-fictional, too easy to mock. But it worked in the way that good branding works, and the article generated an avalanche of letters. In 1973, DeWitt and Neil Graham published the anthology that finally printed the full 137-page thesis, the real one, unsedated, the version Wheeler had filed down 16 years earlier. In 1977, Wheeler and DeWitt got Everett to Austin, Texas to give a talk. It's the one time he came back into the room. Accounts of it are consistent and slightly heartbreaking. An overweight, chain-smoking man in a black suit, drinking through lunch, utterly lucid about the theory, completely uninterested in returning to the field. Wheeler was openly trying to recruit him back into physics. It didn't take. But a young physicist named David Deutsch was in that room, and Deutsch went on to become the theory's most uncompromising advocate, and, in 1985, to write the paper founding the theory of the universal quantum computer, in which he argued that a quantum computer's power is precisely the power of computations distributed across branches. That's the cross-domain bridge that nobody expected. Everett's metaphysics fed directly into what is now a multi-billion-dollar industry. And while you do not need many worlds to build a quantum computer, you should notice how naturally the engineers talk. When people describe a quantum machine exploring many possibilities at once, they are, whether they mean to or not, speaking Everett's language, because it is the only language in which the sentence is straightforwardly true, rather than a picturesque lie. Meanwhile, the cosmologists arrived from a different direction entirely. If you want to describe the quantum state of the entire universe, and inflationary cosmology forces you to, you cannot use an interpretation that requires an external observer to collapse the wave function. There is no outside. There is nobody standing beyond the universe with a measuring device. You need a formulation in which the universe just evolves, on its own, with observers inside it. Everett's formulation is that, not a preference, a structural necessity. So how mainstream is it now? Let me be accurate rather than triumphant, Because this is exactly where science communication tends to cheat.
There is no clean survey of the whole profession, and most physicists never think about interpretation at all, which is itself a Copenhagen victory of sorts. The polls that exist are small, self-selected, and taken at specialist conferences. One from 2011 had Copenhagen around 40% and Everett around 18%. Others, especially among people working in quantum cosmology and quantum information, have put Everett at or near the top. Sean Carroll has written a whole book making the case that it is simply the theory taken seriously, and he is not a fringe figure. So the honest summary is, from a heresy that ended a career, it has become one of the 2 or 3 positions a serious physicist can hold without apology. That is a colossal reversal. It is also not a coronation, and anyone who tells you it's settled is doing to you what the Copenhagen consensus did to Everett. Every bit of it arrived after the funeral. There's one more thing, and it's the reason this story is not only sad. In 2007, the son, Mark Oliver Everett, who by then had spent 15 years as the frontman of the band Eels, writing, as it happens, some of the most unflinching songs about family death in modern rock, made a documentary for the BBC called Parallel Worlds, Parallel Lives. The premise is almost unbearably simple. A man in his 40s, who never knew his father, goes to meet the physicists who did. He sits with Byrne. He goes to Princeton. He talks to people who can explain the universal wave function to him, but who cannot tell him what his father was like at breakfast, because they never saw it either. And there's a scene, the one everybody remembers, where the boxes come out. The moldering cardboard boxes from his own basement. The papers, the drafts, the notes. A rock musician, holding pages of his father's mathematics, trying to reverse engineer a human being from equations, because there was nothing else left to read him from. No letters to his son, no advice, no stories, just the work. At one point, somebody tells him, gently, that his father was a genius, and you can watch the information arrive with no place to go. Because what do you do with that? It doesn't refund anything. And then there's the moment when the physicists explain to him, kindly, what many worlds implies. That in some branch, there's a father who talked to him. And you can see Mark register it, and you can see him decline it. Not angrily, just the way you decline something that is obviously no use. That for me is the whole film. Because here's what I've come to think after all of this, and it's not the take I expected to have. We tell ourselves that the many worlds interpretation is the consoling one. It's the one that shows up in the films where the hero gets to see the other life. Everyone assumes that infinite branches means infinite comfort. Somewhere you took the other job. Somewhere you said the thing you didn't say. Somewhere the illness went into remission. It isn't consoling. It's the opposite of consoling. A theory in which possibilities are lost at least gives you the dignity of a real choice. When the road not taken is genuinely not taken, then what you did mattered, because it was the only thing that happened. The universe was watching, in the sense that the universe was keeping only your version. In Everett's universe, nothing is at stake in that sense. Every alternative is out there, at full resolution, being lived by someone with your memories up to the moment of divergence. The better version of your life is not a fantasy, it's a fact. It is somewhere, right now, actual, complete, and permanently, structurally, unreachably not yours. That's not a multiverse of second chances. That's a multiverse in which you are the version you got,
and the accounting is closed. Hugh Everett understood something at 26 that the rest of the field took 40 years to catch up to. And I don't think it saved him from anything. I think it may have done the reverse. I think a man who genuinely believes that nothing is ever lost has no reason to go and get anything back. Why apologize to your daughter in this branch? There's a branch where you already did. Why come home early tonight? Somewhere you did. The theory that abolishes loss also abolishes urgency. And urgency, it turns out, is most of what love is made of in practice. It's the thing that gets you off the chair. He proved that everything survives, and he was the least present person in his own house. One last thing. When Hugh Everett was 12 years old, living in Washington, he wrote a letter to Albert Einstein. A kid's letter about a kid's paradox. The old chestnut about what happens when an irresistible force meets an immovable object. And Einstein wrote back. It's a short, warm, funny note, and the gist of it is, there is no such thing as an irresistible force, and no such thing as an immovable object. But there does seem to be a very stubborn boy who has fought his way through difficulties he invented entirely for himself. Difficulties he invented entirely for himself. The most successful physicist of the 20th century looked at a 12-year-old and diagnosed him in one sentence. And then the boy went and spent his whole life proving it correct. He told them to throw him away, and they did. The ashes sat in a filing cabinet for a while because his wife couldn't quite do it. And then they went out with the household garbage, exactly as instructed. There is no grave. There is no marker. There is nowhere to go. But if the man was right, and he might have been right, then the universe did not comply. It kept every version. The one who published the full thesis unedited and was celebrated for it. The one who never went to Copenhagen. The one who put down the drink. The one who came home early one evening in 1968 and asked his daughter what she was reading. All of them are still out there. All of them are permanent. Every single one of them is more real than a memory and more solid than a hope. And not one of them is this one. That's the part nobody tells you about infinite worlds. It doesn't console you. It just means the better version of your life exists, in full, and is not available to you.